All right, we are done with chapter 6 and we're moving on to chapter 7, which is just integration techniques. And I like this chapter. I think it's a lot simpler than 6.2 and 6.3. It's really just a kind of tool bag of integration techniques. So we don't have to worry about volumes anymore, measuring radiuses and heights of cylinders, things like that. It's just straight up integration. So we're just learning some techniques to solve some more difficult integrals. And remember what we said from the introduction or the kind of review of integration, that we have this problem where if we're integrating one function times another, fx times gx, we have this problem that the integral of f times g is not equal to, we can't split it up like this. It's not integral of f times integral of g. Okay, so these are not equal. Okay. All right, so a lot of our integration techniques are dealing with this kind of issue, and we saw an example of that with U substitution. U substitution was one way we got around this problem. Okay, so U substitution works in some cases, but it's not going to work in every case. So we're going to develop a new technique in this section, integration by parts. Okay, so to motivate integration by parts, remember that the product rule for derivatives. If I want to take the derivative of this left side, if I'm taking derivative of fx times gx, well, that's going to be f prime of x times g of x plus f of x times g prime of x. Okay. And now remember the fundamental theorem of calculus. What we basically need to know is that if we integrate, let's focus on this left side here. If we integrate this left side, the integral and the derivative are going to cancel out. Okay, so I integrate this left side. Let's just kind of move down the left side for a second. If I integrate that left side, I'm just going to be left with f of x times g of x. Okay, but going back up to this line, okay, if I integrate the left side, well, I need to be integrating the right side as well, right? I need to, if I do something to one side of the equation, I have to do it to the other side of the equation. Okay. So this integral should be equal to this stuff over here, okay? The integral of f prime of x g of x plus the integral of f of x g prime of x, okay? So nothing surprising over here, but if I rearrange this line a little bit, this second line, if I rearrange that, I get a useful tool for integration. So let's subtract this from both sides. And I'm going to end up with this third line. F of x g of x minus the integral of f prime of x g of x times g of x equals the integral of f of x times g of x, g prime of x. All right. So to recap, we have this formula. Okay. The integral of f of x times g prime of x equals f of x g of x, okay, where this is just a function, okay, it's not inside of an integral or anything. It's actually going to be an antiderivative, okay? So this is just a function, and then we're subtracting this indefinite integral here, okay? So it's really just undoing the product rule and kind of rearranging some stuff a little bit. There's a kind of particular shorthand for integration by parts. We usually write integral of u dv equals uv minus v du, where this u and this dv, these are both functions. Okay, and then these are functions. Okay, so everything's functions. Same thing with these. Okay, so this isn't yeah, I won't get into the kind of philosophical outlook on this dv. Just think of it as the function, okay? So in particular, this integration by parts works when we have one function times the derivative of another, okay? When I have this setup, I know I can integrate this thing and get this. Okay. The trick is going to be recognizing that we actually have this situation. Okay. And it's not something that's going to pop out to you. It's usually you're going to try it and see if it works. Okay. So let's try it with this integral here. So let's try it with this integral, the indefinite integral of x times ln of x dx, okay? So we'll set aside what should be the u and what should be the dv for now. I'll tell you off the bat. Let's try and use u equals, we'll use u as ln of x, and we'll say our dv is equal to x. Okay, so remember our formula. We have integral u dv minus equals uv minus v du. Okay, all right. So I'm saying what I have is, say ln of x is our u and x is our dv. Okay, what should be on the other side of my equal sign? Well, the u should stay the same. So my first thing, I should still have that ln of x. And then instead of dv, I should have v. So I need, what's the antiderivative of x? Well, that'd be x squared over 2, right? Okay, so that's going to be my v. Okay, so I got my u, I got my v. Now I need to subtract the integral of v du. Okay, well, v, like I just said, is x squared over 2. And then what's du? What's the derivative of ln of x? Well, that would just be 1 over x, right? And now I need to integrate that thing. Okay. So let's continue on this line. Okay, just rewriting what we have. We can simplify this integral a little bit, right? I got x squared over 2 times 1 over x. Well, that simplifies as 1/2 times x dx. Okay, and then I can integrate this thing. I know how to integrate this, right? Okay, and now once I've gotten rid of all my equal signs, I'll put this constant integration there. And then again, let's just simplify. Okay, so this should be my antiderivative. Okay, so this is just a fairly straightforward integration technique. We're starting with a indefinite integral that we don't know how to solve, and we're basically looking at it through as it's kind of like a product rule. We kind of think of it as part of a product rule problem and undo that product rule just using this formula. Okay, integral of u dv equals uv minus integral v to u. All right, and then we just plug our u and v into that formula and we integrate something easier. This integral is usually going to be easier than our original, and we get our antiderivative. Okay. Now you might be asking, well, how do we choose what's u and what's dv? Okay. There's a handy little rule. You don't have to use this. It's not a, I wouldn't say it's a rule. It's more of a guideline. It's fairly useful. It's this acronym LIATE, Liate. Okay, and those letters stand for logarithm, inverse trig, algebraic, trig, exponential. Okay, so what does all this mean? Okay, your integral is usually gonna, it's got functions. Okay, and these functions usually fall into one of these categories. And whatever's higher up in this list gets priority to be u. Okay, so let's say we have a logarithm and an inverse trig function in the same integral. Okay. Okay. Uh, okay. So let's say I have a logarithm and an inverse trig thing, inverse trig function. Well, my log should be u and my inverse trig should be dv. If I had algebraic being something like a polynomial, something like that. If I had an algebraic and an exponential function, exponential being something like e to the x, okay, well, the algebraic should be my u, and then the exponential should be my dv. Okay, so that's how this guideline works. Uh, that's a good guideline. You know, experiment with it and see what works for you. The way I kind of think about this is, if I have a problem like this, x ln of x, I ask myself, okay, if if I took the derivative of one of these functions, would that make things easier for me? So I have x. If I kind of think about it, well, if one function if I took the derivative of one function and the antiderivative of another, would that make things easier? So I look at something like x ln of x and I say, well, hey, if I had derivative of x, which would just be 1, and or actually it would be the other way. I would ask myself, well, if I had antiderivative of x, if I had x squared over 2, and I had the derivative of ln of x, which would be 1 over x, would that be easier to solve? And well, that's going to simplify to 1/2 x, right? And I can integrate that. So that's the kind of logic I have, but that's something maybe that you develop with time and experience. So maybe that's not something you can just look at it and see it. So if you need something more formal and more kind of formulaic, I guess this is a good tool to remember, this liate. All right. So now let's try and use this rule and apply it to this integral here. Okay, so I got x times e to the x. Okay, and I'm trying to take the derivative of that. Oh, skipped ahead. All right, so what should be my u, what should be my dv? Well, x is a very simple polynomial, or so that would fall into the category of algebraic. And then we got e to the x, which we said a moment ago is an exponential. So let's see, what should be my u, what should be my dv? Well, let's see, a comes before e in this little guideline. So my x should be my u, and then my e to the x should be my dv. Okay, and remember we're using this formula. Okay, so let's see. This is my integral u dv. What should be on the other side of my equal sign? Okay, let's just write this again. Okay, what should be on the other side of my equal sign? What's uv? Well, u is just x, and then if e to the x is dv, what's v? What's the antiderivative of e to the x? Well, that's just e to the x again. Okay. Now I subtract the integral of v du. Well, we said e to the x is v. What's du? Well, that would just be derivative of x, which is just 1. Okay. And if I'm multiplying by, I can just ignore that multiply by 1, right? It's the same thing as just having integral of e to the x. All right, so this is what I have. And then let's try and solve this integral. Well, that's just e to the x again. And now that I've gotten rid of all my integral signs, I can add my c for my constant of integration. Okay, so this should be my final answer. This should be my antiderivative. Okay, so not too bad. Well, there's just a couple tricky examples. we're going to cover the case for definite integrals as well. But before we move on, I want to make one little comment that it hasn't been an issue yet, but when you're subtracting this integral, okay, we have a minus sign here, and then we're subtracting this integral. If this antiderivative here involves negatives, we got to make sure to distribute this negative. Okay, so that's a common mistake. I'll make sure we see an example like that by the end. But if you don't see it, just keep that in mind. Okay, so everything we've done so far has been for indefinite integrals, right? We didn't have bounds in our integral. We have integration by parts for definite integrals as well. So if my original integral has bounds, we're doing a definite integral from a to b. It's the same process, but now, okay, this part here, f of x times g of x, which is the same as my u times v, that's an antiderivative, and I need to evaluate that. I need to plug in bounds. I need to plug in those bounds a to b. And then I'm subtracting my integral from a to b of f prime of x dx. Okay. In the kind of standard notation of integration by parts, we have the integral from a to b of u dv equals uv evaluated from a to b minus the integral from a to b of v du. Okay, so let's try that definite integral. Okay, let's try this definite integral, x times ln of x from 1 to 2. Okay. Remember, we're using the formula AB, u dv equals uv evaluated from a to b minus integral from a to b v du. Okay, so I can still use the same Lie rule. Okay, so let's see, I got a log and I got an algebraic, so what should be my u? My ln of x should be my u. Okay, so let's just rearrange the first integral. Instead of writing x ln of x, I'll write ln of x times x, same thing. Okay, but now I got my u dv. That's not necessary, that's just something I'm doing to make it more clear for you guys. Okay, so what should be my uv? Well, u is just that ln of x, and what should be my v? Well, if x is dv, then v is going to be x squared over 2. And now I need to evaluate this from 2 to 1. Okay, and I'm subtracting the integral from 1 to 2 of, let's see, I need v du, right? So I need x squared over 2. And then what would du be? That would be derivative of ln of x, 1 over x dx. Okay. I can simplify that integral, right? Okay, x squared over 2 times 1 over x, that's x over 2. Okay. And I'll say that we have a choice that we could evaluate. We could plug in these bounds to this first antiderivative and find an actual number, and then find this number separately. But what I usually do is I'm going to actually find this antiderivative first, and then I'm just going to plug my bounds and all in at the end. Okay. I'll show you what I mean. So let's solve this integral now. Okay, so the first part is unchanged. Okay, and then the antiderivative of x over 2, that would be x squared over 4. And then we should evaluate that from 2 to 1 as well, right? Well, now I'm evaluating this from 1 to 2 and this from 1 to 2. So instead of doing that, what I'll do is I'll just put it all together and evaluate it all at once. Same thing. Okay. So now let's plug this stuff in. Let's plug in these bounds. Okay, so I have ln of 2, 4 over 2, so times 2, minus 4 over 4, which is 1. Okay, and then I'm subtracting, let's see, ln of 1 is 0, so 0 times 1 over 2, so 0, and then minus 1/4, right? So simplified, that's equal to ln of 2 times 2, so 2 ln of 2, minus 1 plus 1/4, so minus 3/4. So that should be my final answer. Okay, so not too much trickier for definite integrals. Just remember that we're evaluating here and here, okay, and we can combine it all and evaluate it at the end. That's fine. The next level of trickiness for integration by parts is integrating by parts multiple times. We might get some integrals that if we do integration by parts once, we still haven't found an answer, and we might have to do it multiple times. So an example would be t squared times e to the power t dt. Okay. All right, so let's try integration by parts. Okay, so using my Lie rule, if let's see, I have a algebraic and I have an exponential. So my u should be t squared and my dv should be e to the power t. Okay. So let's see what happens when we try this approach. Okay, so my uv would be t squared. Well, integral antiderivative of e to the t is just e to the t. So my uv would be t squared e to the t. Then I would subtract integral v du, which would be e to the t. Okay, du would just be 2t. Okay. Now, all right, this is fine. This is an antiderivative, but the problem is now I have this derivative here, and I don't know how to solve this right off the bat, right? There's no simple antiderivative for this. In fact, if I'm just looking at this, excuse me, let's just look at this integral on the right side. Let's look at that in isolation. If I was just looking at that box, how would I approach that? Well, I would try an integration by parts on that, right? That's exactly what we're going to do. Okay, so let's kind of keep track of what we have so far. So far we're here. Okay, and then I'll end up with this integral that I don't really know how to solve. Well, maybe it pops out to me that I should try integration by parts again. Okay, so let's try and figure out what this integral in particular is. Right, so let's write that now. Okay, so I got e to the t times 2t dt. All right, integration by parts. Again, this is algebraic. This is exponential. So again, this should be my u and this should be my dv. Okay. Typically, when we do integration by parts multiple times, the same family of stuff is always going to be the u's, and the same family of stuff is always going to be my dv's. Meaning, if in the beginning of my problem, I pick e to the t to be my dv, then it's going to be the same throughout my problem. Okay, I wouldn't want to switch it up in this step and say, okay, well now my et is going to be u, and then 2t is going to be my dv. Okay, then it's going to get into this kind of endless loop of going back and forth, and you're not going to make any progress. You can try that out for yourselves and experiment with that if you want to kind of see how that can go wrong. But if not, take my word for it that, again, we want this 2t to be our u and this et to be our dv. Okay. Then integration by parts for this integral gives me, all right, 2t e to the t minus integral et times 2. All right. And then now I can solve this integral, right? This integral here is 2e to the t. All right. Now, this stuff is the integral of this. All right. And this came from here. So now let's plug everything we have in. So again, remember my original problem was this, t squared e to the t dt. In our first box, this box up here, we said, okay, that's equal to t squared e to the t minus this integral. Well, now we know that integral is equal to, and let's put it in parentheses to keep track of negatives. We know that integral is equal to 2t e to the t minus 2 e to the t. Okay. And then I don't have any integral signs anymore. I can put my constant of integration here. But now this is what I was saying, that we need to be careful of the negatives. We need to make sure we distribute the negatives, okay? So now just make sure to distribute those negatives properly, okay? I have a minus sign here and then a minus sign there. That's going to become a plus, right? So this should be my final answer. Okay, so my view on when to do integration by parts multiple times, similar to my logic when I was thinking about what to make my u and what to make my dv. I say, okay, I'm looking at this integral, this integrand, this stuff inside the integral, and I'm asking myself, all right, maybe it's clear to me at this point that it's integration by parts multiple times. Maybe it's not. I say, hey, if I took derivative of t squared, what would happen? Would my integral get any easier? Well, I say, hey, if I had t e to the t instead, kind of the derivative of t squared times e to the t, is that integral easier? Well, it's not, I can't do it right off the bat, but it's getting closer, right? I've reduced the power of t a little bit. Then I say, what if I did that again? What would I end up with? Well, I would end up with integral e to the t. Okay, and I can do that integral. Okay, so that's my logic when approaching these integration by parts multiple times. They're usually going to be like I won't say usually. Many times it's going to be a polynomial like t squared or something times an exponential or a trig function. But it's not exclusively that. But a lot of times it's that. And when we have a trig function, we have a special technique that we'll use that I'll show you, and then we'll be done with this video. So let's say I have this integral, e to the power of 2x times sine of x dx. Okay. This is going to be an integration by parts multiple times again. So let's try and go through integration by parts. All right, using our Lie rule, again, we would have, all right, trig comes before exponential, so sine of x should be my u, e to the 2x should be my dv. Okay, so let's just kind of rewrite that like this. All right, so what's my u and v? Well, u is just sine of x. What's my what's my v? If e to the 2x is my dv, what's my v? Okay. Antiderivative of e to the 2x would be e to the 2x over 2. Okay. And then I'm subtracting e to the 2x over 2. What's the derivative of sine? Cosine. Okay. So now I have this integral, and again, I'm not done, right? I can't solve this integral easily, but I'm looking at it and I say, hey, maybe this is another integration by parts. So now let's keep track of this line, but let's try and figure out what this integral is. Okay. E to the 2x over 2 cosine of x dx. Again, using integration by parts. And in fact, let's go ahead and write it. In this order. Same integral, just change the order a little bit. Okay. U dv. All right, so uv would be cosine of x. All right, and then I would have e to the 2x over 4, right? Because I'm dividing by 2 and then dividing by 2 again. And then I'd have e to the 2x over 4. What's the derivative of cosine? Negative sine. Okay. Does this help me? Yes. It might not be apparent at first, but it does. All right. So now let's combine these two lines. All right. So in my first line, my original problem, I'm saying sine of x e to the 2x dx, that's equal to sine of x e to the 2x over 2 minus this integral here. Okay, and from the second line, we know, well, that integral is equal to this stuff. Okay, so let's plug that in. And let's put it in parentheses so we can remember to distribute our negatives. Okay, and let's well, I'll save that. Okay, and now let's go ahead and simplify. All right, so sine of x, just distribute our negatives and such. Okay, minus cosine of x e to the 2x over 4. And distributing this negative to here, okay, we'd have plus e to the 2x over 4 times negative sine of x dx. All right. And I can pull this negative outside the integral, right? And change that plus to a minus. So let's just, instead of rewriting the whole line, I'll just get rid of this negative and change that to a minus. And then I can pull out this 1/4, right? I can pull out that denominator and write this. Okay. Now, notice that this integral is my original integral, right? That's what I started with here. These are the same thing. So let's add this 1/4 times my integral to both sides, okay? So when I do that, I'm going to end up with 5 over 4 times my original integral, right? And then what am I going to be left with on the right side? I'm going to have the sine of x e to the 2x over 2 minus cosine of x e to the 2x over 4. And then this is going to get canceled out completely on the right side. And then I'm going to have my constant of integration, since I don't have any more integral signs on the right side. And then remember that my original problem was finding just this integral by itself, right? There was no, in my original problem, there was no 5 over 4 out front. So I want to get rid of that from the left side. Well, how do I do that? I multiply both sides by 4 over 5. Okay, the multiplying by a constant doesn't affect my constant of integration. That's still just going to be plus c. And then the rest is just simplifying. Okay, so I have 4 over 5, and then I got a 1/2 here. So I could simplify that as, what, 2 over 5 sine of x e to the 2x. And then I got a 4 over 5, and then divide by 4 here. So I could simplify that as minus 1/5 cosine of x e to the 2x plus c. And that would be my final answer. That's my antiderivative. So that's the little trick we use when we're doing integration by parts multiple times with like trig stuff involved. Okay, we're going to do it twice, and then we should end up with our original integral. Let's see, our original integral times a constant on the right side, and then we're going to move that original integral over and then divide out that constant. Okay, so that's our little trick for integration by parts multiple times with trig stuff. All right, and that really covers all the hard examples or hard concepts from this section. This section's fairly straightforward. It's definitely a technique worth hammering into your brains because it's extremely common. You're going to be using it whatever level of math you continue towards. You're going to be using it all up to the end of your math careers. So definitely worth knowing. Problem video to come.